Hi, this is a video about periodic trends, and you guys have been learning about them with that simulation. And this hopefully will help everything kind of tie together and make sense. So the first thing is the periodic table is awesome. It's repeating, and it's all based on the quantum numbers essentially, but it also, elements that are in the same group are going to chemically and physically behave similarly. So family, sometimes they call groups family because they're related to one another. And then there's also the repeating pattern, these trends that happen. So one of them is that you covered already, is atomic radius. So just to review that as we get bigger, going down a group, the atoms get bigger. And the reason why is because you keep adding another level. This is n equals 1. Then we're on the second level away, then the third, then the fourth. And then, so I think that one makes sense. But then when you go through left to right, they get smaller. And that one's a little weird because they're adding protons. They're getting bigger, but their size is smaller. And that's because you're increasing the power, the positiveness of the nucleus without adding any levels of electrons. So like if I'm in n equals 4, I'm going to, starting at potassium and then going over to like bromine, I haven't added any energy levels. So I'm gaining electrons, but they're still, I haven't gone beyond n equals 4. And then also, like bromine has 35 protons to pull harder on those electrons and pull them in, compared to potassium only has 19. There's also something now called effective nuclear charge, which is essentially, if you have an atom and you have that nucleus, and then it's kind of like if you were to go to a concert or a football game and there's all these people in the way, and you're way out here, and in the middle, in your way are all these other electrons. So what we call that is electron shielding. It's shielding this electron from feeling the pull of the nucleus. It's also, we talk about effective nuclear charge, so this electron doesn't feel the nuclear charge as strongly. And you can actually calculate this. We won't, but all of these core electrons are getting in the way of this outer electron feeling the positive pull of the nucleus. So, to summarize atomic radius, as you go, and you could draw this in your notes, like a periodic table. As I go down, the radius is going to be getting bigger, increases. And as I go across, the radius gets smaller. So, keeping in mind what I just said about electron shielding and effective nuclear charge, this is a new trend now. You didn't see this one in the simulation. So this is something called electronegativity. And electronegativity is the ability of an atom to attract electrons from another when they're in a bond together. The values are going to range from 0 to 4.0. So here's an atom. Let's say its electronegativity is 3.0. It's able to pull electrons towards itself fairly well. It would want to gain electrons. Let's look at it in terms of the shielding. So here we have, over here is an oxygen atom, and oxygen has a higher electronegativity than sulfur because it doesn't have as many electrons in the way. It's smaller. So if the electrons have to pick, am I going to go over here or am I going to go here? and this is the positive nucleus, they're going to want to go where there's less electron shielding, where the atom is smaller, because they're going to be able to feel the pull of that nucleus better. Another way to look at electronegativity is it's like you have two different atoms. Let's say this is fluorine with 4.0, and then let's say this is barium, which is 0.9. So the fluorine has a much higher electronegativity, a much more able to pull electrons towards itself. I wanted to show you that the electronegativity values are actually on your periodic table. So right down here, that smaller number is the value. So you can see like fluorine is the most electronegative, and so these are the top electronegative elements. And then when you go over to the metals, so everything to the left of the staircase are metals. These guys have lower electronegativities. They don't want to pull electrons towards them. They actually want to give up electrons, and that's why they conduct electricity so well. So the non-metals are the ones over here to the right of the stairs, have higher electronegativities. So here's the trend again. So as I go across, remember the atoms are getting smaller, so there's a greater pull from the nucleus, so the electronegativities are going to get higher towards fluorine. And then we aren't really looking at the noble gases because they don't want to bond. They're already so stable. So a lot of these trends, we just kind of ignore them. They don't even have, well, I guess the top three don't even have a listed electronegativity. And then the bottom ones, they do, but they're not really going to bond and have those electrons to be pulling anyways. And then francium's going to be the lowest. So it's like the extremes of the table. So as I go to the right, they get bigger, and as I go down, electronegativities get smaller. Ionization energy is the amount of energy it takes to pull off an outer valence electron. So it's always going to require some energy, but some atoms are more willing to give up those electrons, and it doesn't take as much energy. And this is something you did explore in that simulation. So if I were, and this is from the simulation, like if I were going to pull this electron or pull this electron, which one's going to be easier to pull? And rubidium and iodine are in the same period, so they have the same number of energy levels. But you can see that because iodine has more stronger positive nucleus, it pulls that whole atom in closer, has a smaller radius. So it's harder to pull that electron off, which means it has a higher ionization energy than over here. And iodine is a non-metal. They don't want to lose electrons, they want to gain electrons. Rubidium doesn't feel this nucleus as much, so it's easier to pull that electron off. So it'll have a low ionization energy. Another analogy of this would be like if you were at a football game and you're way up in the nosebleed or concert, you're more likely to leave, go to, get popcorn, maybe leave even before the end of the game, because it's just not as interesting as if you're closer, more sucked into the game or the concert. So ionization energy, it increases as we go to the right. With this time, we still don't really include the noble gases, but they would have really high ionization energies because they don't want to give up their electrons because they're so stable. But as I go to the right, it's harder and harder to remove a valence electron. As I go down, it's easier and easier because as I go down, remember, I keep getting bigger and further from the nucleus, more electron shielding, so easier to pull an electron off. All right, so just to summarize, and you want to have this probably in your notes somewhere handy. If we were to look at a periodic table, and we'll just make ours a little rectangle, we'll talk about, so as I go to the right, and as I go down. So as I go to the right, the atomic radius is going to go down. And as I go down, the atomic radius will go up. They get bigger as I go down. They get smaller as I go to the right. Electronegativity is going to increase as I go to the right towards fluorine. And as I go down, electronegativity is going to decrease because they're getting bigger as I go down towards francium. And then ionization energy also does the same trend as electronegativity. So as I go to the right, it takes more energy to pull off an electron. And as I go down, it takes less. So ionization energy and electronegativity are inversely related to the atomic radius. You can think of it that way. Just make sure that you know the meaning of them, but the trend for electronegativity and ionization is they are the same. All right, that's all I have.